Okay, so I'm back with the cholesterol and I'm going to have a look at adding in the gender and the abdominal fat into the model. So you could look at this with some graphs first. I do recommend that. So you could go to your chart builder and you could look at some box plots. You could look at means and confidence intervals. You could possibly look at both the variables together in this plot. So our outcome would be cholesterol. Doesn't matter which way around you do them. They're just depends which way you prefer to interpret it. In this case, I think I'll put the abdominal fat on the x-axis and I'll put gender as the cluster color. We might want to zoom in a bit there. Let me just change the y-axis because it's change that scale to let's go 4. That'll do. And actually, if you want them bigger, don't be afraid to change the chart size. And even these little doodads, you can change them as well. I just want the little dots, I'm going to change them bigger. Size, nice and big. Okay. So I've got my plot there. What can we see? We can see that for females in blue, if you've got a low level of abdominal fat, you have lower cholesterol. If you've got some abdominal fat, your cholesterol level is going up. This is on average. And for the severe abdominal fat, it's going up a tiny bit more. But if we have a look at these confidence intervals, I'm not sure that this is statistically significant, whereas there does seem to be a real difference between the some and the low. So that's for females. For males, we've got a similar pattern, that they're a little bit higher in the low. So the men were a little bit higher with the cholesterol overall, but it's going up more for the abdominal fat. So it looks like the abdominal fat is having more of an effect on the men than it is on the women. And this is an interaction. You can't tell if an interaction is statistically significant just from looking at the plot. You really, really need to run the model. And I think we might be able to get it to do a proper interaction plot, not with the means and the confidence intervals. There's nothing wrong with this plot. It can be a little easier to interpret if we have some lines on there, that's all. So for general linear model, univariate, we would add in our gender and abdominal fat. Now if we don't do anything to the model, it will add in the interaction term by default. That's what this full factorial means. It means it adds in all the interaction terms. If you're not comfortable with the interaction, or you don't think the interaction is important, you can just build your own model where you just select everything and say you're only interested in the main effects. So we'll do that first and then we'll come back and add the interaction in. Now I'm going to leave my residuals with the unstandardized predicted values and our standardized residuals. I should have taken that plot out, it's just too small to... So what have we got? So again, the null hypothesis for each line is that there is no relationship or no difference. So for gender, it'd be that there is no difference in cholesterol between males and females once these other variables have been adjusted for. We've got a very small p-value, so we've got very strong evidence against that null hypothesis, and therefore gender is important. And the same with ab fat, and again, age is not important. So maybe we actually go straight and take out that age and stop looking at it. Run the model again, and so everything is still significant here. So to add the interaction in and have a look at that, we'll go to general univariate. I just want to take out that plot that it keeps doing, that one. So in the model, to add the interaction in, we would select both our Well, because we've only got 2, you could just select full factorial and it will do it. You need to be a little bit careful with this option, because if you have more than 2 factors, the model can get overly complicated without you realizing that you're testing all these different things. So often it's easier to build your own model. So gender and abfat and an interaction. Use abfat times gender. Continue. So the thing to remember here with your dialog box is that anything which is continuous is a covariate. That should be a scale variable. Any variable which is categorical should be a factor and go in this first box. And for this course, we're not looking at the difference between fixed and random factors. Just put everything in the fixed factor box and that's fine. Okay. So we've got here, and you'll notice that, well, I'm hoping that you're noticing that every time you run a slightly different model, these significance or p-values do change a little bit. So before we had a 0.001 and now it's 0.000, because every time you change something, everything shifts around just a little bit. So usually you only add or subtract one variable at a time. There's a couple of ways you can do it. You might like to start with one variable and add them in one at a time, seeing if they're significant. Or you can start with everything and then take them out if they're not significant, one at a time. So the null hypothesis here for interaction is that there is no interaction between gender and abdominal fat. We have got very strong evidence against that, and therefore there is an interaction. And from the plots we could see that the nature of the interaction, or how to interpret it, is that the abdominal fat is having more of an effect on the males than the females. So it's worse for the men to have a high level of abdominal fat in terms of their cholesterol. And I probably better just reiterate that this is a fake data set on fake people on the island. It's not real data, so don't draw any real life conclusions from this. Go and do your own literature review on the actual science. But for our fake people, this is what the effect is. The other thing that we're interested in here is the R-squared value. So this is how much of the variation in cholesterol can we explain with our variables here. And we can explain quite a lot, probably because they're not real people. If you had data on real people, I think your R-squared would be way, way lower. Typically, humans have a huge amount of variation in pretty much anything you want to measure. The only time I've seen really consistent data on people is to do with athletes and, you know, running times and swim times, because high performing athletes are fairly consistent. But just for general health data, you'll find it very messy. If you wanted to actually build an equation out of this so that you could make a prediction, then that's what these beta values would be. So to read this off, it would say that cholesterol is equal to a starting value of 3.66, then a little adjustment downwards for females, little adjustments downwards for the levels of abdominal fat, an adjustment upwards for weight, 0.034 for every extra kilo, and then we've got these interaction terms. You get this extra bump depending on what combination of abdominal fat and gender you have. It's not always intuitive to read these values off. You can see that this is actually a bump upwards for females with low fat, but that can depend a little bit on how the rest of the model works its way out. So I would usually suggest that in interpreting the interaction, you go back to the plot and have a look at it. I'm trying to remember if SPSS will give us an interaction plot. Probably, so you could do this one. Probably the line chart will do it too if you want that joined up. But I think you can join up the other plot. No, that is not helpful at all. I think you can probably, to this other graph, I think you can add lines to it. But you can have a play around with that and see that. But this would be what you need to interpret that. So that was our model.